Hello students, welcome to Concepts of Physics with Irfan. Students, as we have started our first year physics, and last time we discussed vectors, unit vectors and graphical method to add two or more vectors. So today we are going to study resolution of vectors. So students, before we will go toward that concept, let us take an example that a mass, let's call that as m, is acted upon by a force, and that force is pointing in that direction, right? Now obviously this is the only net force over here, so this mass will be moving in upward direction. Let's take another example. Over here we are having two frictionless pulleys, and with the help of those two pulleys we are going to apply force on the same mass. Now as you can see, due to these pulleys, the direction of these two forces, let's call this one as F1 and the other one as F2. So these two forces, they are actually pointing in different direction. But you know one thing, the mass over here, it is neither going to follow any of these two directions. Instead it will follow a straight upward direction, and that is only possible if the resultant of these two forces generate a kind of net force along this direction. Now why we are discussing such example? Because you know here with the help of two forces we can generate a force which is actually moving an object in a totally different direction. So we can say that a force can have two such components which when joined together can produce the original force. So that's why our today's lecture is very important, because we are having a wide range of application in everyday life. Now what does mean by this resolution of vector? So dear students, resolution is actually splitting or breaking anything, right? So in case of resolution of vector, we are going to split a vector into its part, right? So it can be defined as, it is the splitting of vector into two or more components. Okay, so if we can split or break a vector into two or more components, that process is what we call the resolution of a vector. And these components, if such component, when they are perpendicular to one another, at that time such component will be called as rectangular component, right? Rectangular component. So after resolving a vector, if the new component, or if the component which we are going to get after the resolution, if they are mutually perpendicular, then such components will be called as rectangular components. So students, let us take an example. Let's say that this is our xy plane, a two-dimensional plane, right? And a vector, this is the origin, and we are representing the position of a point with a vector, and that vector is, let's say we are having a vector A, right? This vector is actually representing the position of this point with respect to the origin. Okay, now it is lying in xy plane, in a two-dimensional plane. If we want to split such a vector into its component, what we can do, we can draw a perpendicular line along both axes. So when we draw a perpendicular line along x-axis, let's say this perpendicular line cuts the x-axis at point C, and along y-axis this perpendicular component cut the y-axis along at point D, right? Now dropping a kind of perpendicular line is the same as if we shine a kind of light at this point, then we will get the projection of this vector along x-axis, and that much will be the projection, right? So this will be the projection. Similarly, if we shine a kind of light from this point, so again we are going to get the projection of this vector along y-axis, and this much will be the projection, right? Okay. Now these projections along x and y axis, we call this projection as the component of original vector, and as this is along x axis, so we can call it as ax, and it is a vector, right? And similarly, this is along y axis, we can call this component as ay. Now you can see both these two are parallel, right? They are having the same length, so we can even call this one as ay. So this is ay. Okay. Now, component is actually the effectiveness of a vector along any axis, that how much effective a force is along x or y axis will be its component, right? So now this vector here, it is making an angle theta with the x-axis, right? Now how we can find these components in terms of the original vector? So for that we can draw the triangle OCP, right? So we can draw the triangle OCP over here. So you can see it is a right angle triangles because we have draw perpendicular line on x-axis. So this is OCP. Okay, and this side it is showing the original vector, right? And this is the x component and this is the y component, ay. I am only writing their magnitude, right? So far I am dropping the arrow sign. Okay, now as it is a right angle, so we can use trigonometric ratios in order to relate vector and their its component, right? So from trigonometric ratios we know that cos theta is actually equal to base over hypotenuse, and from here you can see that this is the right angle, this is the angle theta, so this is the adjacent side which is the base, and here in this case the base is the x component of the vector, and the hypotenuse is the side opposite to the right angle, so we are having A as our hypotenuse, and perpendicular the side which is opposite to the angle theta, so we are having ay as our perpendicular, right? So from here we can write cos theta is equal to, so we can replace ax instead of base, instead of hypotenuse we can replace a. Okay, so we can rearrange it and we can find ax. So ax will be equal to a times of cos theta. Let's call this as equation A. Similarly, we can use sin theta, and sin theta is perpendicular over hypotenuse. So sin theta will be equal to ay over a, and this implies that ay would be equal to a sin theta. So let's call this as equation B. Okay, now using these two equations we can write vector A in terms of its component. Okay. Okay students, as you can see over here, these two components, they are actually being added according to head to tail rule, right? So this is actually the resultant of these two vectors. So from head to tail rule we can write, so from head to tail rule we can write vector A is actually equal to ax plus ay, right? And now we have found ax in terms of the original vector and cosine, and ay in terms of a and cosine. So we can replace these values in, let's call this equation as C, right? So we can replace equation 1 and equation A and B in equation C. So we will get A would be equal to So here instead of ax we can replace a cos theta. Okay, now we know that the unit vector along x-axis is I. Similarly, the unit vector along y-axis is j cap. So we can write unit vector I in order to represent this term in vector form, right? So ay can be represented as a sine theta unit vector j. So we want to avoid the arrow, right, by inserting I hat and j hat. Okay, so let's call this as equation D. Right, now we can find the magnitude of this vector in terms of its component, and we can find the angle which the vector is making with the x-axis, right? So in order to find its magnitude of a vector, again we can consider this triangle OCP, right? Now from this triangle you can see that it is a right angle triangle, so we can apply Pythagoras theorem, and Pythagoras theorem relates all these three terms. So from Pythagoras theorem, a square, and we are interested in its magnitude, so we can omit the arrow sign. It will be equal to hypotenuse square will be equal to base square plus perpendicular square. That is the statement of Pythagoras theorem. So ax square, right, absolute value shows the magnitude, and ay square. So the magnitude of x square plus the magnitude of y square gives us the magnitude of the resultant vector, right? So we can take square root, and our result will be magnitude of a will be equal to square root of ax square plus ay square. Okay, so that's how we can find the magnitude. And we can find the direction theta using another trigonometric ratio, that is tangent theta. So we know that tangent theta is actually the ratio of perpendicular over base. So tangent theta, this is the magnitude, right? So it is the magnitude, and for direction we know that tangent theta is actually equal to perpendicular over hypotenuse. So in this case we are having ay over ax. So theta would be equal to tangent inverse of ay over ax. Okay. Now students, we have done the resolution of vector for two-dimensional space, two-dimensional coordinates, sorry. If we represent a vector in space, because normally the real world or the real vector space has 3 dimensions, right? So for that what we are going to do is, let us consider that this blue marker, it is pointing in this direction out of the board, and this is representing the z-axis, and the black marker over here, it is pointing in space, right? So we can find its x component by dropping a perpendicular along x-axis. We can find its y component by dropping a perpendicular along y-axis, and similarly we can find the z component by dropping a perpendicular along z-axis. Okay, and once we found x, y and z component, then we can add all those components using this equation in order to find the magnitude of the resultant vector. So we have to include another component in this equation, and that would be az square, right? What about direction? Now as you can see that this vector over here, it is making certain angle with x-axis and also with y-axis and z-axis. So over here we are having 3 different angles, because it is not necessary that all these angles will be equal, right? So we can have any measured angle along any axis. Okay, now let's say that in 3 dimensions, so for 3 dimension, for 3-dimensional. Let us consider this is the x-axis, this is the y-axis, and this is the z-axis, right? Okay, now if a vector is pointing in space, and for that we can draw a kind of 3-dimensional box, right? Okay, now let's say that this is the vector pointing in space, making an angle alpha with the x-axis, beta with the y-axis, and let me represent gamma with the z-axis. So it is making 3 different angles along with 3 mutually perpendicular axes. And the unit vector along x-axis will be I cap, along y-axis will be j cap, and along z-axis will be k cap, right? Now how we are going to find the direction for such a vector? So we can use any of these angles, but if we are going to find alpha, we have to use x, y plane. In order to use beta, or in order to find beta, we can use y, z plane, and for gamma we can use x, z plane, right? So we will be using the same formula in order to find the angle for the 3-dimension. Okay, now we are going to discuss addition of vector using rectangular components. If we are having 2 or more vectors, how we are going to add such vectors? By first finding their components, right? So last time actually we used head to tail rule, but that was a kind of geometrical or graphical method. So today using the component or rectangular component, we actually stress on mathematics. So it is a kind of analytical method. So let us start addition of vector using rectangular component. Okay students, so let's start addition of vector using rectangular component. So this is analytical method, so it involves mathematics. Method, right? Okay, now in order to add 2 vectors, let us draw those vectors separately first. So let's say this is the first vector, and we call this vector as A, right? Making an angle theta A with the x-axis. This is x and y-axis. And let's draw the second vector. Okay, so from the origin, let's take this vector as B, and it is making an angle theta B with the x-axis, right? Now we want to add 2 such vectors by using their rectangular components. So first we have to draw both these vectors on a single plane, and we have to apply head to tail rule, right? So by placing the tail of second vector on the head of first vector, and then we have to join the tail of first with the head of last vector. Now, but in this method we are interested in finding the component of individual vectors, and in terms of their component we are going to find the resultant vector, right? So let us see that how we are going to do that. Okay, so this is the origin, right? And let us represent vector A. So this is vector A making an angle theta A with the x-axis, and over here we are going to place vector B, right? And this is vector B. Okay, and if we draw a virtual x-axis, so this is angle theta B with the x-axis. Now in order to find the resultant vector, we have to join the tail of first with the head of last. So this will be our resultant vector R. Okay. Now you can see that vector A has an effective component along x and y axis, because it is lying in xy plane. If a vector is lying in a plane, so it must have an effective component both along x and y axis, right? So we can find its x component by dropping a perpendicular along x axis. So let's say this is the x component of A. We call this AX, right? It is a vector. Similarly, its y component we called AY. What about the x component of B? So we can draw a perpendicular over here. So this is the x component of vector B, because both these are parallel and having the same length. So so this will be the x component of vector B, and this will be the y component, right? So this will be the y component. So let me draw this over here. So this is BY. Okay. Now if we draw the component of the resultant vector, so we can get its x and y component, and the x component would be this much, Rx, right? Similarly, this will be the y component of resultant vector up to this point, so Ry. So from the figure we can see that this, if we add Ax and Bx, we are going to get Rx, right? So we can write that the resultant component along x-axis is actually the summation of x component of A and x component of B. Let's call this equation A. Similarly, the resultant vector along y-axis is summation of y component of A and y component of B. Let's call this equation B. Okay, now from head to tail rule, we can see that if we extend this vector, that is actually the x component of resultant vector, then we can join the y component from this point, and eventually we are going to get the resultant vector. So from head to tail rule, we can even write that R vector is actually the summation of Rx and Ry, right? Okay, now let's call this as C. We can replace Rx and Ry using equation A and B, so that we will get R will be equal to Ax plus Bx. I want to drop the arrow, so I can use unit vector I cap plus, instead of Ry we can replace this value Ay plus By, right? So in order to represent direction we can use J cap. Okay, so this is how we can find the resultant vector using rectangular component of two vectors, right? Now what about its magnitude? Okay, so in order to find its magnitude and direction, we can use the same formula. So it is starting here, right? From here we are going to start over here. Okay, it's a right angle triangle, and using Pythagoras theorem we can find the magnitude, and the magnitude of R will be equal to square root of Rx square plus Ry square, right? Now we can replace Rx and Ry, so the magnitude of resultant vector will be Ax plus Bx and Ay plus By. And we can extend this expression if we are having more than two vectors. So if let's say we are adding three vectors using rectangular component, so we can include an extra component over here, and let's call that as Cx and Cy, right? And if we perform the same process in 3 dimension, then we have to include z-axis as well, right? Okay, now and here we have to write the square. Okay, now what about direction? So for direction we use tangent theta, and that would be equal to Ry divided by Rx, and thus theta would be equal to tangent inverse of Ry. We are having a y plus by. This is for two vectors in two dimension. We can extend this concept to 3 or more vectors, and even we can extend it to 3-dimensional coordinate system, right? So tangent inverse of a y plus by over ax plus bx, right? So that's how we are going to find the angle theta r. We call this angle as theta r because this is the angle which the resultant vector is making with the x-axis, and it gives us the direction of the resultant vector, right? Okay, so these two expressions are very important, and this one over here, because using these two expressions we can find the magnitude and direction for any vectors using its rectangular component. Okay, now sometime the vector they point in another quadrant. If a vector is lying in some other quadrant, then how we are going to find the angle? So let us consider that let us say that this is our xy plane, for theta r we use such an xy plane which have 4 quadrants. So this is x, this is y, this is negative x, and this is negative y, right? This is the first quadrant. Okay, so this is the second quadrant, this is the third quadrant, and this one is the fourth quadrant. Okay, when a vector is lying in the first quadrant making an angle theta with the x-axis, then at that time the angle of the resultant vector theta r would be equal to theta. And when a vector will be lying in the first quadrant, when both the x and y component of that vector are positive, like if let's say that if the x component is greater than 0 and y component is greater than 0, both are positive, at that time the vector will be lying in the first quadrant. Now if x component is less than 0 and y component is greater than 0, it means x is negative, at that time the vector will lie in the second quadrant. Now this is the angle theta. Now we know that we have discussed this in our previous classes, that we will always measure angle from the positive x-axis in the anti-clockwise direction. So this would be the angle theta r, right? So how we are going to find this angle in such a case when the vector lie in the second quadrant? So we know that the total angle subtended on a line is 180 degrees. So in order to find theta r, what we have to do? We have to subtract this angle theta from 180 degree. Okay, now let us take another example. Now in this case the vector is lying in the third quadrant theta, making an angle theta with the x-axis, right? Now it is only possible when both x and y are negative, right? So both are less than 0. Over here we can measure the total angle from the positive x-axis. Now we know that from this point to here the total angle will be 180. So in order to find theta r, we have to add this angle with 180 degree, right? Because the angle subtended at a straight line will be 180 degree. Okay, the last case, when x is greater than 0, positive, but y is less than 0. So x is greater than 0 and y is less than 0. So in such a case our vector will be lying in the fourth quadrant, and let's say it is making an angle theta with the x-axis. Now we know that we can measure angle anti-clockwise. So for measuring theta r, what we are going to do? We are going to from here you can see when we will complete a cycle, the total angle would be 360 degree. So if we subtract this theta from 360, we will get theta r. So here we are going to subtract theta from this 360 degree. Okay, thus we can find the correct value for theta r when the vector is lying in different plane. Okay, so this was all about resolution of vector and addition of vector using rectangular component.